For me, it's a great pleasure to be here. Of course, correctly, I am in charge of IT education, but I have a very strong technical background, and I've been in charge for storage for many, many years during the LHC data taking. So I really have my heart still with storage. So in scientific computing, the question is what has changed recently? And of course, in science is extremely well consolidated. And the laws of physics, mathematics, chemistry, statistics don't change very often. But computers have really never improved so fast as in the last decades. Of course, as I have a long history, I started with 8-bit computers, then 16-bit computers, and when we moved to 32-bit computers, nobody would ever think that a computer could have 4 GB of RAM, at the time where the RAM was counted in kilobytes. Now, in the last decades, and probably just in the previous accelerator, the CPU performance moved from megahertz to now gigahertz, and the number of CPU available was few hundreds. Now for the LHC experiments, we have 500,000 core available to do the scientific research. The storage moved from few gigabytes to several petabytes, and the possibility to collect and transfer data across wide area network moved from megabit to hundreds of gigabits. So here you can see the 3 pillars of scientific computing: processing data, storage, and networking. And we had an incredible improvement in the last years. If just imagine that we would have only 3 orders of magnitude improvement in the normal technology, we would have today trains traveling at 100,000 kilometers per hour. And with 5 orders of magnitude, we would have trains going at the speed of light. So what has changed? Clearly, this was also mentioned this morning, there has been this exponential growth of computing, and this for a fixed investment. Now, given that computing has now the highest return of investment, the amount of money going in computer has significantly increased, and this brings even more than exponential growth. And it can be a good or a bad news. Probably it's a good news. We are just at the beginning. I'm not the first person saying this today, but I'm absolutely convinced that there are incredible progress that is just behind the corner. We can, on everything, if we talk about processor, with the new GPUs, FPGAs. And a significant example from my field is storage. 20 years ago, we decommissioned the accelerator that was in the LHC tunnel. So it was an accelerator 27 kilometers long. It was called LEP. And the total amount of data accumulated during the physics and this more than 10 years of operation were 100 terabytes. And these 100 terabytes were occupying the entire CERN data center. Now, today, these 100 terabytes can fit in less than 3 tape cartridges, which can fit in the drawer of my office. Today, the CERN data center has 1 exabyte, so which is 1,000,000 terabytes of accumulated data. And so the question is how many years we have to wait before all this data can again fit in my drawer? And the answer is rather straightforward. It's today. Because if you take a micro SD card that has 132 cubic millimeters of volume, and you see that one exabyte only requires 33 liters. So maybe it's not just my drawer, maybe the file cabinet I have in my office. Now, this is just in terms of storage density. But the interesting thing is that with this, when you have large data, you can start to stripe the data, so to write in parallel. And so you can really have much, much higher performance. And of course, by adding error correction code, you can really be resilient to failure of storage elements. So you can really reach arbitrary performance, and arbitrary reliability. So, of course, the only limit is the interfaces to which you access the data, and that's why you see all the investment in, for example, now PCI Express, etc. In addition, you don't consume power, so it's also a way to reduce the megawatts that we have heard this morning data center requires. So today, this is just too expensive, but it's just a matter of time, because there is no reason that silicium would cost more than the kind of hardware that is today necessary in building, for example, hard disks. So, are we aware of what is coming in the coming years, etc.? And the general population is not aware of these changes. And I will give you a quick proof. So this is a survey that I have run because with my students that were in the last year of Master of Finance in the University of Lausanne. And these are very well-educated persons. So it's not just random people. So I asked them if they could tell me what was the distance between Lausanne and Zurich, and I offered 4 questions: 200 meters, 200 kilometers, 200,000 kilometers, or 200 million kilometers. And guess what? Everybody got the right answer, because there are 3 orders of magnitude distance. So common sense, even if you don't know what is the distance between the 2 cities, could be immediately found. But what about questions about on computing? How many transistors are in the Xbox One X main chip? Only 1 student out of 5 got the correct answer, and the most popular answer had 3 order magnitude error. So it's just like estimating that the train would go at 1 kilometer per hour instead of 100. How many IP addresses are possible? So that's a nasty networking questions. And we only had 1 correct answer. And what is more concerning is that the most popular answer had 20 order of magnitude error. So it's probably less than a nanometer per year, the speed of the train. So the problem is that where are the main risks? Is that cannot differentiate science from science fiction. It's hard to differentiate what is possible from what is impossible, but this now applies to many, many other fields of society, differentiating news from fake news, photos from AI-generated photos, etc. So the consequence of losing the awareness of what computers can do is that also dependencies cannot easily be identified. It becomes difficult to maintain digital sovereignty. So, of course, what is the digital sovereignty we have already heard this morning is related to identify which digital activities can be outsourced while maintaining the authority to self-govern. So must be in control of the computing infrastructure necessary to the business. Now, we have been discussing about cloud computing, cloud storage, infrastructure as a service, platform as a service, software as a service, proprietary and licensed software. And clearly, these are all some sort of outsourcing of your computing infrastructure. And I would like to focus briefly on the 2 aspects, the software and the data. But before, just a personal interpretation of what are the requirements for outsourcing, to do a successful outsourcing, and why this exists. It's clearly when you have an activity that is not strategic, and it's not part of your core business, that the activity has clear and established standard interfaces. And of course, there are multiple independent vendors implementing these standards. So that allow you to switch from one solution to another. If the 3 requirements are satisfied, you can have an exit strategy. If a supplier fails, you have other ones, etc. And you also are in a strong position to negotiate contracts, negotiate licenses. And of course, you can make significant savings. Because outsourcing, when done properly, will bring significant savings. Otherwise, licensed and proprietary software would not exist. Now, But of course, if any of the three requirements is missing, then access to your data or the use of the software that is necessary for your company to operate is at risk. And there are many, many scenarios that can happen. You know, you can be locked in with a particular vendor. The company, the vendor can fail, can disappear. The contract may fail, or you may not be in a position to renew the contract that you had already, that previously signed. Laws can change. You may be subject to remote jurisdictions. And you can clearly lose access to your own data or to the usage of the software that you need. And this morning, we also heard about the kill switch, especially when you're using cloud solutions. The loss can be instantaneous from one day to another. And for example, there has been, there are many, many examples of this has already happened. I think I remember during the previous Trump mandate, I think it was Venezuela lost all the access to the Adobe Cloud following an executive order from one day to another. So let's drill down in data. Now, unfortunately, this is what I put on my slide, but this morning I have learned that, because these are the data from 2023, but Jan said that it's already 12 trillion, the turnover of the GAFAM company. And it's interesting because data is more and more strategic. And you have also seen the shift, for example, from Microsoft that was always trying to sell you software. But now what they are interested in is to get at your data. So very often, that's, you cannot buy Office without having OneDrive. And when you use Office, it constantly offers you to save the data in OneDrive, so that it really to try to basically take all your possible data. And now, so this brings me to a few words about using cloud storage, because cloud storage is very successful. It's easy to understand. It's therefore easy to sell. And it's a simple storage model. All data go into the same container. It's uniform. It's simple, easy to manage. You don't have to do data management, and can provide sufficient level of performance and reliability. Now, for large repositories, this simple approach becomes simplistic. And the reason, for example, that we have in science, in large experiments, is that there are really multiple types of data, which requires different quality of service. So the three examples, which are the most obvious, is that you have the raw data that are coming out of the experiment that must be analyzed. So these are data that are extremely valuable, that you don't want to lose, so you want high reliability, and that you need to distribute to thousands of cores to be analyzed. And you can afford to have the storage to be expensive, because these are small quantities of data. Because as soon as you have processed, what you need is just to preserve the data, but you don't need the high performance. So you need the lowest possible cost solution that is reliable. You don't need performance. The third example is derived data, data that can be rebuilt, that you need, for example, configuration data that all the nodes need to access. So it's already replicated in tens of thousands of cores. So if you lose some, you just get a copy from another node, or you can even recalculate it. So here you need high performance, low cost, because it's a significant amount of storage, but you have minimal reliability, so no extra copy. So this corner always shows the various options that you have, that you can build using different type of hardware, and you can choose to have something that is fast or very reliable or cheap, but you cannot not have all three. But with software, you can position yourself anywhere in this triangle. And cloud storage is always on the upper part, the expensive solution, fast and reliable, but of course, as soon as you scale up in size, this becomes unaffordable. In fact, in science, these are examples of some experiments that have been going on at CERN, and you really see that the data is constantly moving from various data pools. And the reason why there are all these data pools is because there is a significant difference in quality of service. So what are the options? Of course, there are always the two extremes. One is to build your own infrastructure with the full software stack, and there you have huge fixed cost. And so if you are below the critical mass, it's too expensive or unaffordable. At the opposite extreme, you just move everything on the cloud. You only have the variable cost. So, and for small volumes, this is much, much cheaper than clearly having your own infrastructure. You have no data management necessary, but really you need to assess the risk. And as you can never or very hardly audit the cloud provider, this is extremely difficult. Of course, you can mitigate the risk by having multiple cloud providers, so you can replicate across multiple clouds. But of course, you have to do your own data management, or also keep a copy on premise. So you need an infrastructure. So basically, at the end, you have the fixed cost. Even given that you have a backup copy, it can be less reliable. So you can save on this. But again, you have to do your own data management. Now, if we move to software, software is clearly strategic. It's strategic for the business, and it's something that is flexible, and that's why all companies invest somewhere in software. Now, the more you invest, the more complex it becomes, and that's where you need the top skills in the long term. And now, of course, we talk, now a quick digression, we talk about artificial intelligence. Now, I remember in biology, some of the definition of life was that life is a property of matter which is attained when the matter goes beyond a certain complexity. And I think that with software, we call it AI because now software has reached a complexity where the single individual cannot understand it anymore completely, and therefore it becomes something lively and intelligent. It's similar to our LHC machine, which when you hear the operators talking about the machine, they say, "Oh, this morning is not very cooperating." You know, they treat it as a human being, as something alive, you know, as it would have some sentiment and passion. So back to the talk. So 3 choices: you write your own software, closed or open source. This gives an economic advantage, as the competitors do not have access to your software. Of course, you pay all the cost. But of course, you can also be in open source, which is clearly a strong strategy. And given that you are leading so fast and you have the competencies so that no one can overtake you. Or you use open source, so you just take what exists and you customize the software for your needs. So you pay only the customization cost. Competitors have access to your software. But the economic advantage really comes from your business, your company, the fact that you have better products, better skills, you have better support, better services, and so which is your business. And of course, the last option is using proprietary licensed software. Costs are easy to estimate. Customization are also possible because these can be purchased. And the competitive advantage comes while your license remains cheap. But in this scenario, it's clear that you have to share the profit of the company with the software vendor. And in particular, beware about the vendor lock-in. And I will come back in a second on this. So on the open source approach, custom development are built on top of established interoperable open source solutions. And that's the important warning. Remember that it's not free, in the sense that you have to pay for the support and for the custom development. And it's important to have staff in your company that understands the code. So you have to also invest in people. And the interesting thing is that the more you invest, the more you are in a position to control and influence the software governance. So that you can also steer the direction where the open source is going. So that's coming back to the necessity of having skilled employees. So because when designing a custom architecture, you must have experienced architects, which are expensive. And it's important to ensure that employees must have the technical expertise then rather than relying on contractors for support. And I also would like to stress that it is important to maintain the awareness of the ongoing computing evolution or revolution at all levels of the staff in the company. So not just the IT people, but it's also important that the management of the company really understands where computing is going. Now, back to lock-in and the fact of the risk with proprietary software. It was already mentioned in previous presentation also this morning that the license cost can increase suddenly because they add features that you may not need. But in any case, all software vendors that I know, they have a plan to increase revenues by at least 10% every year. Software companies that does not grow is a company that is doomed. So if the market expands by 10%, then everything is okay. But when the market is saturated, immediately they have to raise the license cost. So, and this is incompatible if you are running a business that is a stable business with more or less consolidated revenues. And so license costs constantly on the rise. And so in this scenario, if your revenues are fixed, the share of your profit that you, the profit that you have to share with the software vendor increase every year. So at CERN, a few words for the large scientific projects. The open source approach is working very well in scientific research. But also the complete on-premise solutions. So a complete data center architecture today can be built using only open source solutions. And by the way, also Azure and Google are doing exactly the same. This leaves the use of proprietary software just in the tool. So you have some particular needs, there is tool, so you can use, that's the only scenario where you use licensed software in a data center. But the critical mass to build a successful infrastructure is beyond what a small institute can afford. So there is the open source approach, but also the consortium approach, which is really the best practice to collaborate on well-focused projects that guarantee maintaining ownership of your critical activities at the minimum cost. So here I would like to mention what we have everywhere in Europe are called, for example, for the NREN, so the National Education and Research Network, which connects all the university and all the research centers. In Italy we have GAR, in France is Renater, I think. In Switzerland, we have Switch, which are consortium controlled by the university, which provide data centers that are shared across the entire country at really minimal cost. So this brings me to the conclusion. So business will be always under very strong marketing pressure to outsource IT technology. The recommendation is always to outsource only standard activities, well-defined and interoperable. Do not outsource your own business, that's clearly. The open source approach is an excellent practice to maintain sovereignty and minimum cost, because you can control the software cost, and especially if you grow, you will not have license cost increasing proportional to your business. So you will not have to share your profit with the proprietary software vendors. Everything learned in hard science during traditional studies is still valid. So there is still a good motivation to do scientific studies, of course, but technology is moving extremely fast. Computer and networks can do much more today than a few years ago, will do even more in the coming years, and the solutions that were computationally unfeasible in the past become possible today. So as we cannot fight progress, artificial intelligence and machine learning applications are everywhere. But it's interesting because sometimes we talk, oh, we need to invest in artificial intelligence. But this is just a huge container of possible solutions. And the solutions that you have for language model have nothing to do with the solution for autonomous driving or scientific research or weather forecast. So there is an entire world of new opportunities that is just opening, thanks to what computers can do now. Of course, this can bring several improvements, plenty of new business opportunity. Of course, ethical consequence must be understood and handled. And that's my last statement, that insourcing critical activities ensure maintaining skills in-house. And so the education in IT is really strategic in the coming years. Thank you very much.